In this video, I'd like to go over the general discussion about these limiting velocity of these falling body problems. So this is a usual setup. There it's an object with mass m, and there's a gravity toward to whatever the direction. So let's say it's a rectilinear motion. So it goes down this way. And the force created by the gravity is assumed to be constant. So it's mg by Newton's law of motion. But another interesting thing here is we're assuming is air resistance. So as it's moved toward down and going through the air, and there will be air drag, and depending on the velocity only. So if it's moving fast, then you can imagine the air resistance, air drag is harder, and if the velocity is smaller, then you can imagine air drag this body is experiencing is smaller. Not necessarily directly proportional, but there's this dependence on the magnitude of the velocity. It is Newton's second law of motion. This connects the acceleration with the force that is exerted to this body. So the law is that force exerted to this body is defined pretty much to be the mass times the acceleration. If it increases the velocity, we simply assume there's some force exerted to that, whether you see those forces or not. That's the idea behind this law of motion. We don't see strings attached to anything, but it is moving faster. We assume something is pushing it. So here's how you analyze. So here's the force. That force mg, the gravitational force, is there, and whatever this air drag, depending only on the velocity, is represented by this fv. It's written here. So they work against each other. Constant. This is we usually assume this is a positive value, as f of v is a positive value and it's worked against this gravitational force. Now, for example, if this is a lot, then you can see the force is little, therefore the velocity maybe gets smaller. Then once it gets smaller, and this is weak and this is picks up again, so it pulls down harder, so velocity picks it up. So in that way, kind of see what's happening, but it is not so easy to actually predict exactly what's happening to the VT for continuously as time increases. So we're connecting now these forces by Newton's law of motions, m times the acceleration. So we can write this as the differential equation of v, first order. Because of this generality here, it's not necessarily linear though. So we may write it in the standard form by dividing both sides by this constant m, then we arrived at here in this form. And typically textbook starts with a simple example that this drag force, air drag, is directly proportional to the velocity. So Fv can be kV this time. Let me introduce this kind of big theorem in this differential equation, especially in the first course. This is cited a lot. Not sure this can be always proved in that or introduced properly in the first year course, but it is something you need to know. This is a first order nonlinear standard form differential equation with the initial condition. Then it says existence and uniqueness theorem says there is one and only one solution around t equals 0. At some point I'm going to specify the meaning of this around t equals 0. It means there's a small neighborhood at least around t equals 0 such that there is a solution and that is the only solution with this initial condition here. But you might have noticed this v prime is here and the right hand side is basically all in terms of v, so just typical separable equation. From that separable equation we also know the existence and uniqueness theorem. And you can get a specific idea about what we mean by this around, but we're also going to go to the detail of it. But main purpose of this video is discussing this limiting velocity, the phenomenon of the limiting velocity. As you let that one go with the initial velocity, with that much of the air drag involved, with a constant gravitational force, if you let that one just go, free fall, then it turns out there's a limiting velocity. As time approaches infinity, the velocity becomes just stable and becomes some velocity, not decreasing or increasing or keep oscillating from back and forth. So that's what we wanted to calculate, what we wanted to discuss here in this video. In many mathematics problems, if you simply assume that there is this limiting velocity, sometimes it's really easy to calculate. But if you think about, another puzzling part of this whole situation is understanding why this limiting velocity exists. So often this question is sometimes boring, but here I think it's a very interesting question. First, we're going to focus on how to calculate that limiting velocity, but after that, which will be a short discussion after that, we're going to think about why this limiting velocity exists, and which is important part of understanding this physical phenomenon here. The following part I'm not going to prove, but using the mean value theorem or something like that, you can easily prove that if this limiting velocity exists, time goes, this velocity doesn't change, so Vt value doesn't change. As you can see, rate of change of that value is probably 0. So it must be the case that V prime is going to be 0 as t approaches infinity if the velocity doesn't change. Now this is our differential equation, and we're going to operate with this operator limit t approaches infinity because this quantity is the same. And this is a constant. Now we assume this exists. We assume V exists. That's the whole assumption here. Assuming the continuity of F, this will make sense. Now we've seen that this approach is 0, so that's going to be 0. And this part is going to be V of V infinity, the limiting velocity. Here we use the continuity of this function is cut out here. Now I'm showing this part, the continuity of this function f. So we have this equation. So this yields an equation f of v infinity must satisfy v infinity, the limiting velocity must satisfy this equation. If this f is simple enough, and you can calculate this v infinity easily. For example, like this, if fv is the direct proportional k times v, like this, then v infinity is mg over k. This limiting velocity must be this gravitational force divided by the proportionality of air drag. So we're going to make this simple. Suppose, for example, fv has finitely manager. This is wrong, and it's not this. This one is 0. The 0 of this polynomial is the correct one. These v1 and v2, the numbers that makes f of v1 equal to gm. So in this case here, we only have 1, 0 for f of v minus gm. So I wrote it in there. I was running out of room, so I had to write it over here. I hope you can see this gm is this part, and fv is this function part of the velocity. Is not the f has finitely many 0. This one has finitely many 0. That's what I meant. So v1 and v2 are a number of velocities that makes this whole thing 0, so that these two things are equal to each other. We suppose that they're finitely many, and v1 and v2 are two of them right next to each other. So there's no more zeros in between v1 and v2. So the idea is that if we start with somewhere in between v1 and v2, and we're going to see this limiting velocity phenomenon in between and here. The first thing I want you to notice is that this v1 and v2, what this vk is standing for, and if you think about constant function, vt being always a constant to this function, that function is a solution to our differential equation. Let me show you the differential equation. Sorry, it shook a little bit. I'm showing you the differential equation again. Now we chose this v1 such that these two things are equal to each other. So that's going to be obviously 0. But because it's a constant function, the derivative is going to be 0 anyway. So that's 0. So if this constant function is obviously a solution to our differential equation. Second thing I want you to notice is that this existence and uniqueness theorem implies that all the other solutions will never intersect these two solutions we're looking at. Because if they intersect, and they're different function, when they intersect, that gives your initial condition, and you started from there. If you have two different solutions, that makes no sense because of the uniqueness theorem. So let me show you the picture. For example, here are the two situations. This is V1 and V2. Those are the constant solution. Suppose these are the different solutions of the differential equation. If they intersect like that or like that, however you do it, you can take that as an initial condition. You start from there and think about a solution of functions that satisfy this initial condition and differential equation. You can see there are two different functions, and this violates the existence and uniqueness theorem. And think about it here. Take that as an initial condition, and there are two functions satisfying this initial condition and differential equation that contradicts the conclusion of existence uniqueness theorem. So you cannot intersect, and that's one fact that comes out of the existence and uniqueness. So in the next part of the video, I'd like to go over the general discussion of the existence of a limiting velocity. So first we start with the initial velocity that is not equal to those two zeros, v1 and v2. This is not right now limiting velocity. These are the two velocities right next to each other that makes the right hand side 0. So we don't know if these are the limiting velocity or not. But the v0 is in between those two. And we show the solution of this vt will have a limiting velocity or either v1 or v2. So rather than going over a specific example that's going to lead us to complicated integral, I extracted this detailed part of the existence uniqueness theorem that you don't see in the main statement of the theorem that is available in the textbook. This is the part of the proof, and I extracted it out. So right hand side is this two variable function t and v. In this case here, there's no t outside. It's just only in terms of v. So our capital F tv is going to be the constant minus this constant times function only in terms of v. So that's the setting. The first derivative is written in terms of the main variable time and our unknown function v. In this theorem, we calculate this partial derivative of this one. Here it will be just the derivative of v because it's only in terms of v. So derivative of this one is 0. Derivative of that one remains there as a constant multiple. Derivative of that one with respect to v will be, of course, the f prime of v. And in this existence and uniqueness theorem, they calculate the maximum of this value. Okay? So here there's no t, so it's only about this v value, v1 and v2. And we know the solution of this one and exists in between v1 and v2 because it cannot intersect v1 and v2, which was discussed earlier. So we know the v remains v1 and v2, and the theorem in the proof of the theorem requires to calculate maximum value of this partial derivative while t and v varies in here, but t is not involved in here, only v is involved in here, so this is sufficient condition. And again, in that theorem, it is used that this number m is used in the following sense, that equation has only one and only one solution in this setting if t remains in between this range. v2 minus v1 came from this the ranges of v value divided by this maximum. And this will guarantee us to have a good control on something, which is keeping this v value in between v1 and v2. In the process of proving all this thing, we do not have the existence and uniqueness theorem. They're in the process of proving it. So with that one, they have a control that v will be in between v1 and v2 if t is small enough like this. So that's the technical condition so that they can calculate something easily. So in our case here, since there is no t is involved in here, so it doesn't matter where t is centered at. Not only at the 0, if t is in between t values is around this central point to c, not necessarily 0, we have a same condition. So not only this, so we have a general statement. If t is around c by this radius, then there's a one and only one solution, not necessarily at 0. It's all because right hand side here there is no t involved, but only v. So these numbers is right now is difficult to understand if you didn't study the proof of existence and uniqueness theorem, but it's some of the facts that we're going to use to understand the phenomena of limiting velocity of this falling body problem. So we have this concrete neighborhood calculation that we can calculate between what value and what value. This we have a solution for this differential equation. If you think about it, what we are discussing is the existence of the v infinity, which requires t to be larger and larger, right? So this is going to be actually the major problem. So this is how we actually overcome this problem with this result. First, we start from 0, and we have this differential equation, and the theorem says that we have a solution around this small neighborhood like this. So we start from t equals 0, only up to this number v2 minus v1 divided by m, we have a solution in here. And this theorem does not guarantee we have a solution further. So we have a solution up to here. To continue our solution, we can start from here, that n value, or somewhere in here, a little bit before, doesn't matter. So that can be a new central point, not 0, but we can start from c, because again, our differential equation does not involve any t value in here. We can apply this one again, get a new radius of existence. So starting from here, we can have a same amount of radius to the right or left. So we can extend our solution. Because it's continuously extended, this whole thing is actually a single function. And uniqueness theorem again guarantees that it must be, there's only one solution actually in between 0 and all the way up to the second point over here. And again, from here we can use this theorem again and extend it and further. By doing this infinitely many times, we can reach all the infinity, and that's still a unique solution to all the way to the positive infinity. Although the existence of uniqueness theorem guarantees a very small region, that small region can be repeated over and over to the right, and relying on the fact that our right-hand side of the standard differential equation, standard form differential equation, does not have t in it. And this bound is independent of location of t values. So let me remind you what we have just accomplished is that using the existence uniqueness theorem, a little detailed version, that the exact radius of existence for the t value, using that we were able to show that this initial value problem has solution starting from 0 to all the way to the infinity, right? Not just around t equals 0. So we have that much. We have a solution, well, which is, if you think about this as a physical problem, the body will keep moving and will have a velocity. Therefore, the existence of a velocity in that physical setting is obvious, but think about it sometimes, and the physicists rely on mathematical implication. So if you really just look into this mathematical formula, if the mathematical solution gives you some weird complex solution, something like that, we have to sometimes accept that and conclude that, okay, eventually this body will disappear, because that's what mathematical formula implies. So if you think the whole point is that sometimes if you really wanted to see how this mathematical consequence is, you can't just rely on physical intuition. Sometimes these days modern physics is very counterintuitive and just relying on mathematical consequences. Now remember, those two v1 and v2 are the numbers that makes this right-hand side of the differential equation 0, not necessarily their limiting velocity. And we're starting from the initial velocity such that this is not 0. Of course, if we start from there by an existence uniqueness theorem, that the velocity will remain just like that, because the horizontal line is the only solution starting from there. So suppose we chose initial velocity that is not the v1 and v2, but is in between v1 and v2. So it must be either positive or negative. So I'm supposing it's a positive case this time. The negative case has no significance at all, so our discussion will be just carried over to the negative case as well. We talked about this before. The solutions of this one exist all the way to the infinity, will never intersect the horizontal lines v1 and v2. This is the consequence of the existence and uniqueness theorem. So this value, and hence it cannot change its sign. It's because v1 and v2 are two neighboring zeros of this right hand side, and vt and exists, and it never crosses this horizontal line, so it's trapped in between and here. When it changes sign, it's going to hit the 0 and continuously changing from v value to something else. So if it changes sign, it must be hitting v2 or v1. So therefore, because it cannot intersect any of those, it cannot change its sign. It's trapped in between these two values. And therefore, the sign remains, in this case, positive here all the time. Now over here, v prime, the right-hand side is a positive. That means v prime is always a positive, and that means it's increasing. So the function is increasing. That's one fact we have. The second fact is that the function is trapped in between v1 and v2, so it cannot exceed v2, but this one keeps increasing. From there, we can conclude v infinity, the limiting velocity exists. We don't know if it is v2 or v1, but because it's increasing and is bounded by this function, then its limiting velocity must exist. In mathematics, this is called the least upper bound property. The values of this thing is getting bigger and bigger, is bounded by that, so there must be this limiting velocity. To some of us, this principle is kind of common sense, but in rigorous development of mathematics, they had to call this type of property something, so it's called the least upper bound property. Alright, so we showed that least v0 must exist when it doesn't exist, and we earlier showed that it had to be this value v1 and v2. In this case, it had to be v2 because it's increasing and heading towards that, and there cannot be any other zeros of this one, which had to be the limiting velocity, which is the earlier discussion. If we assume this one is less than 0, then it corresponds to decreasing, and it's going to be bounded below by this v1, and therefore also by something called same name, least upper bound property, forces the existence of this limiting velocity, and therefore it has to be v1. So that concludes the discussion of the existence of a limiting velocity.